Okay, so we're kind of looked at the overarching plan of Navy medicine. Now we're going to zero in a little bit on Navy nursing, and then we're going to zero in on the nurse candidate program. So NCP, there's your hint, nurse candidate program. This is a lot shorter than the last video than that's the last one.
Congress officially established the Navy Nurse Corps May 13, 1908. However, as early as the War of 1812, volunteers performed nursing duties in places that were often dangerous and required courage in the face of adversity. By October 1908, the Sacred 20, the first women to formally serve as members of the Navy, were preparing for their initial assignments at several naval hospitals. Navy Nurse Corps numbers expanded to 160 by the start of World War I, and they became active in training U.S. nurses overseas and male enlisted medical personnel. After World War I, duties expanded to include regular service on board Navy hospital ships. Navy nurses were on duty during the initial Japanese attack on Pearl Harbor and were vital in preventing further loss of life and limb. Aboard hospital ships, Navy nurses followed the fleet at their assaults and were eventually permitted to go to the beaches with the fighting men to pick up the wounded. By the mid-1940s, flight nurses were graduating after additional training in swimming and rescue missions. Upon graduation, they became active members of a flying team. By the end of the Second World War, more than 10,000 nurses were serving in 6 continents. The Nurse Corps played an important role in both the Korean and Vietnam Wars. Today, Navy nurses are deployed all over the world, participating in humanitarian and combat support missions, as flight nurses, aboard hospital ships and aircraft carriers, boots on ground with the Marine Corps, and in support of special operations.
Okay, so in order to find those nurses to perform all those functions, the Navy has this program called Nurse Candidate Program. We use it to fill almost all of our active duty nursing positions. Okay, so students that are interested in nursing, the Navy, we really need to do a better job of reaching them as sophomores, because to get into this program, that's kind of the time for them to apply as a sophomore, second semester, or as a junior. If they miss the window and don't get into this program, then when they graduate, in order for them to be an active duty nurse, it's very difficult because there's like very few openings. Anyway, the program, they have to be in a BSN program, it has to be accredited by CCNE or ACNE, and you can see the long drawn-out versions up there. Upon completion, they will be commissioned as an ensign in the U.S. Navy Nurse Corps. Okay. So basic requirements, they have to be U.S. citizen, must be able to commission by age 42, so that means graduate from school, pass your licensing, then we commission them. All that has to happen before age 42. And the reason for that is they have to be able to serve 20 years of commissioned service so they can get a retirement. Otherwise, they don't get a retirement. So. Must meet Navy height, weight standards. Again, they have to pass their licensing once they finish schooling. And then we commission them. We send them to some training, which I'll cover in a minute. But what the Navy offers for this program, it's not a scholarship. Okay, so I have to make it very clear to everybody that it doesn't pay for school. We give you money. You do with it whatever you want. Okay, so there's a $10,000 bonus. It's $5,000 up front. 6 months later, you get another $5,000. It is taxable, and then you get $1,000 a month while you finish your degree, up to 24 months. And they spread it out on the normal pay cycle, so it's $500 at the first and $500 on the 15th. The payback time is on active duty, so when you graduate, you will be active duty Navy nurse. That's your full-time job. If you receive benefits for more than 12 months, you owe the Navy 5 years of active duty. If you only receive 12 months worth, then you only owe 4 years of active duty time back to the Navy. So, question most people ask, where will I serve? These are all of the locations, not all encompassing. There's probably some remote locations that are on here, but these are common places that we send folks. I know it's small in here, so we normally, whoever I meet with, I show them on my iPad, zoom in, all that good stuff. But as part of this program, initially you're going to start off either at Navy Medical Center in San Diego or Walter Reed National. It's at the National Center. Naval Medical Center Portsmouth. So either California, Maryland, or Virginia. That's where almost all of them go. After their initial first tour, then all these other locations are open to them. It's negotiation. So one common misconception that people have about the military in general is that you don't have a choice on where you get to go. You do, but yes, at the end of the day, the Navy can decide where you go. But it's a negotiation. We're an employer like anybody else, right? So we have to have openings to send people there. So somebody who wants to go to Hawaii really bad, well, guess what? If there's no opening in Hawaii, you're not going to Hawaii. Okay. Anyway, so the training required after you complete your bachelor's degree, you will attend 5 weeks of training in Newport, Rhode Island. You're going to attend a course called Officer Development School. This course is designed to provide newly commissioned Navy officers with the basic information required to understand Navy culture. It's designed to help create future Navy leaders who support the fleet. All right. So the purpose of this course is, yes, you're a nurse in the Navy, but you're a naval officer first. Okay, so you will be leading people. It's going to vary, you know, how many and what locations, all that stuff. But you have to learn some basics about leadership, and this is where you get that. And then the rest you learn on the job. Obviously, in 5 weeks you can't learn everything you need to know, but during those 5 weeks you'll learn a lot. And it's a lot of death by PowerPoint, just like this. You're going to marching around class to class, just slide or slide or slide. You do a swim test out there. You do a physical readiness test, so that's our 1.5-mile run. You do the curl-ups and the push-ups, and it's pretty much easy training. You're already a commissioned officer when you attend the course, so it's not as bad as regular basic training or officer candidate school. All right, that was an extremely fast version of this program. So what does NCP stand for? Anybody?
Nurse Candidate Program.
Nurse Candidate Program, all right. How much is the bonus?
$10,000.
$10,000. What's the payback for 1 year?
4 years.
4 years, all right. What's the payback for 2 years? 5 years. And how much is the monthly stipend? $1,000. Man, y'all got it. Perfect. Well, look at that. Look at those answers. Look at that. All right, any questions? Again, I'm Lieutenant Stephen Harris. There's my contact info. Reminder, all that stuff needs to go, please. I don't want to take it with me. It's good stocking stuffers if you don't want it for yourself. The pencils, no one ever takes them, so somebody please surprise me and take the pencils. And then just to be the recruiter like you claimed I am, if you know any nurses, these are what the Navy currently needs. For active duty, we're looking for labor and delivery, public health, peri-op, critical care, NICU, pediatric nurse practitioners, family nurse practitioners, and nurse midwives. And in the reserves, we have pretty much the same flavors, except a couple extras there. I thank you for your
the
time.
Navy after this?
There's another cool video. If you get bored later, we can show you that one. It's on the Navy's response to Haiti when they had the earthquake. It's pretty neat stuff. And there's also flyers over there if you're really curious or have anybody that's curious. I know we have one instructor who might have students who possibly might be interested one of these days in these. Feel free to take all of them with you if you want. Just saying.
Just saying.
Cool, thank you.
Thank you.
Oh, that's I wonder if my son will be next. You want to go next? Okay.
I'm passing now the pre-test, pre-class questionnaire. So we have a look at the pre-test first.
Thank you.
Yeah, we have enough. law of conservation of energy. It is a physics or chemistry topic normally presented to high school students, maybe freshman college students. So, who exercised this week? Who did go to the gym? Right, thank you. Well, what are you hoping for when you get on that treadmill or get on that pedal?
Get in
What do you
shape.
want to do?
Burn calories. Burn calories.
Burn calories, yes, exactly. Where is that calorie come from?
Eating.
Stored energy.
From Turkey, hopefully. Okay, yeah, basically, that is a form of energy, and calorie is a unit of energy. So today I'll talk about that. So in the pre-test, we're gonna, if you have a look at the handout, you can see the series of questions here, and I would like participants. I would like someone to tell me what's its energy. One volunteer, please.
Like carbohydrates for your body.
Okay, okay. All right, that's a good answer. The energy here is more related to like a definition of it. That's an example. That's good, thank you. How is energy created? Very good. Energy is neither created or destroyed. It was there and it's going to be here forever. So 3 common type of energy. So go ahead and take some time and write down the answer on your questionnaire. And then is energy limitless? Is there a limitation to energy that's available to us? Can it be transferred? Can it be transformed? So hopefully during this presentation, I will cover some of the topic and something more. And please stop me if you have any question. I like an interactive class. So who I am? My name is Vincent, and I am taking. I'm a chemist by trade. I work in a commercial chemistry lab, so in the beginning we did an introduction already. So, you know, today for this micro teaching, I kind of pull off this from Wikipedia. So on the reference will be on Wikipedia. So that's a free quiz. So the objective of this learning is you need to know what energy is, the definition, the dictionary definition of it. The law of conservation of energy. Some audience had say it's neither created or destroyed, and that's exactly part of the law of conservation of energy. And we talk about where is energy come from, and that's come from the Big Bang, or at least the Big Bang theory. And then we come with 3 different levels or different sizes where we can see energy. We can see the energy before at the smaller than the atom size. And then we can see the energy at the molecular size. And then we can see energy at our size, or basically the macro size for us. And then we talk about the energy pyramid. We're going to also have a case study and some activity. And finally, we will hopefully come back to the post quiz and the question and answer. Any question before we start? All right. So the definition of energy. Energy is, this is from Wikipedia article. So in physics, energy is a property of object which can be transferred or converted to different forms. And then it cannot be created nor destroyed. And there's some example of energy here. So hopefully you have 3 of these listed on your pre-test questionnaire. And this is the very useful form, but also very destructive form, is the nuclear energy, energy of the stars. And we have the ability now to harvest this energy and use the energy to maybe light this classroom. Okay. And then we come to the law of conservation of energy. Most of us are familiar with this from Chemistry 101. The law of conservation of energy states that the total energy of an isolated system is conserved over time. So on our known universe, consider a isolated system. So the energy from the beginning to now, as time progressed through billions and billions of years, that total energy was there, neither created or destroyed. And then we will, next we will see the very important theory now, mostly accepted by the scientific community. Of course, some religious aspect of it may not be agreeable to all, but at least in the scientific sense, in the beginning, that way is time zero. So that's time zero. So at time zeros, there is no mass. It's right here. And then the Big Bang. Probably there's no sound can be here on. We were not there to hear the sound anyway. So, but anyway, they call it the Big Bang, and then that's the flash of energy. It's heat. It's a lot of heat there. And as this expands, as is an explosion, Big Bang, is cooled down. So as time progress, this horizontal axis is a time progress. And then we can see that the brighter it is, the hotter it is. So technically the universe is getting cooler and cooler. That's good for us. Well, so there's no mass here, but eventually something has happened that creates a proton. What is a proton? Anyone? Any volunteer?
Thing in the middle.
Exactly. Basically, a proton, yes. It is one of the subatomic particles that make up of the atoms. The atom is the smallest unit that make up anything around us. Everything is made up of atoms of some elements. So, for example, hydrogen. For example, carbon, which is part of the wood here. Water have hydrogen atom in it, and this is a cartoon of a hydrogen atom. It's very simple. The proton that was created there somehow attract another subatomic particle, the electron, 1,000 times smaller than it. So at this time you form this atom. And then what happened? You can combine these two atoms together and you in something called the nuclear fusion. Anyone heard of nuclear fusion? We tried, yes. Basically, we try to press the two protons together to make something heavier a little bit, double the weight of this atom. It's called the helium. So when you put two hydrogen together, you form helium. But something miracle happened. It generates more energy. Strange enough. Okay. So during this time, you have nuclear fusion happen. This is where you see the stars forming. You see a lot of light given out. And some of that light now we can still observe with the Hubble telescope and other telescope that NASA is launching to the space. And then it gets cooler and cooler, and then you start nuclear fusion. That means at this temperature, at this time, you're no longer making helium from hydrogen. And then basically here you form heavier atoms like iron, something like the silicon, and they combine and cluster together and form planet. Okay. And then of course right now we are in the known universe. So well, anyone recognize this equation? Yes, I actually went down to on the way to Dallas. I kind of like a company having this kind of name too. That company has that name, but they're very famous. It's introduced by Einstein. It is the mass energy equivalent. What does this stand for? The energy here is the heat energy that we saw in the Big Bang. the energy right here. And how can it consolidate and make into a proton, which is something you can weight on the scale. Of course, million of proton you can weigh, but the proton is something you call mass. So something has happened that converts this energy into mass. And it's followed this very simple equation, E equals mc squared. So c is the speed of light in vacuum, is about 300 million meters per second. And when you square that, multiply it with the mass, you get the energy contained within that mass. That's an enormous number of energy. So that's why fusion or fission in a nuclear reactor could generate a lot of energy, and is considered the renewable energy. Question? Okay. Right. So we have talked about the energy of the subatomic level. What if the molecules? What is the molecules? Yeah. Molecules is when you put two atoms together. For example, the bottle of water that have H2O in it. What is H2O? This water, right? And that's basically the energy contained within the bond between those atoms. The two hydrogen and one oxygen have a bond that hold them together. And that energy is contained and it's called enthalpy. It's another name for energy in chemistry. And the enthalpy is follow this simple equation. This is the energy contained within the molecules equal to the enthalpy before subtract the enthalpy initial. After subtract the enthalpy initial. So in the beginning, you have hydrogen and oxygen. Technically, you have very little energy. So when you combine them, you have a final state of energy. You subtract the difference, you get the energy contained within that water molecules. And this is another example of more complex organic structure which have many different bonds. So this molecule can be burned and generate a lot of heat. It could be one of the medicines too. But, so that's the energy contained within the molecules. Let's come up with something bigger, like the sun. The sun is very hot. It has nuclear fusion and fission here. And then, you know what this picture is? Solar flare. What it is it generates a lot of heat and light. And that light carries through space to Earth and irradiate our planet. Gives our planet heat. The heat that is transferred to the planet is follow this simple equation. The energy or the heat energy that transferred equal to the mass of the object that got heated times the specific heat of that object is another number. When you heat something, you start with the initial temperature. And then after you heat it, you end up with a final temperature, hotter. You get hotter. So the difference here in temperature, when you multiply with that specific constant for different material and the mass of that object, you can know how much heat you absorb. Okay? And that is the equation for something our size or planetary size. Okay, so let's talk about the energy pyramid. The sun energy comes to our planet, and it got absorbed by the primary producer. What are those? And plants? Yes, exactly. And then the higher organism are going to consume those primary, like us, and then we will get about 10% of that energy. So we do use energy within our body. And then as we go out, some bigger animals consume the lower and lower. And we probably belong to the apex predator, lions and things like that. We're going to belong to that. So we constantly generate heat. And that's the heat loss. And it lost through the space. Okay. Any question on the pyramid? Okay. This is the case study. And Anyone is a cook around here?
Not if I can help it.
Well, I purposely chose like a vegetarian one because. Okay, so here is the stove, right? Normal stove. You burn methane gas, and that you generate heat, and then that heat is part of it go to the pot and the pan, and then kind of heat up this vegetable for our meal. But most of the heat come out, you radiate out and warm up the environment. That's why you feel warm around a stove, right? Or a fireplace, for that matter. But since this is a case study, we want to look deeper to see what's going on in this simple process, a daily process. Okay, methane. Methane is CH4. It's a natural gas. It has 1 carbon and 4 hydrogen. So it's a molecule. So within this bonding of these atoms of hydrogen and carbon, you have energy stored within them. When you break that bond, you liberate that energy, and that energy comes out as heat. How do you break that bond? You break that bond by reacting with oxygen. So when when you turn the gas on, the gas flow, but then no fire. You need a spark to start that reaction. After that reaction starts, these two will ultimately combine. The heat generated will carry on the next, like a domino effect. As long as you have the fuel, you only burn. And what's the product of that? The product that generates carbon dioxide. Water is like a gas, a steam. And then the heat energy that we use. Any question on this slide? No? Okay, so this is another. So let's have a look at the energy transfer here. So we talk about the energy creation from the chemistry aspect. Now the energy can transfer. It transfer to the pot, it transfer to this metal, it transfer to the wall here, it transfer to the cook who's holding the pot, so you feel warmer. And that is the energy transform and transfer in this case study. Okay, here's the activity. I would like maybe a group of 2 or 3 discuss this and write down your answer. Since this is a science class, you're supposed to do some calculation. So here's the given information. According to this article on the property of methane, 16 grams of methane gas. If you weigh it, you can weigh the gas. 16 grams, it will generate about 1,000 kilojoule. It's like calorie, but in a different scale. So it's the unit of energy. So 16 grams is 1,000 kilojoule. So if you burn 48 grams of it, okay, to cook the dish above, the dish that we saw earlier, and then 2/3 of it was lost to the environment. How much heat was actually transferred to the frying pan and food? Basically, it's called useful or the efficiency of your stuff. So, yeah, go ahead and think about it and jot down your answer.
If this is what cops is like, I'm gonna fail.
And by the way, I've seen many students was seeing the number of words is horrible. For some reason, they feel word
18.
problem. But words should be used to verify the problem, right? So
18 times 1,000?
So 18 times 1,000 would be how much energy it took to actually cook the food in the pan?
18,
16.
16 grams, we generate 1,000 kilojoule. We have 48 grams.
Okay, so if we have
3,000.
2/3, so that's 3,000.
About 1,000.
Be 60,000.
No, about 2,000. 2/3.
But
The question is
two-thirds
how
is lost.
much heat energy was actually
So
transferred to
you got
the frying
1,000
pan
left.
food to
Oh,
cook
how
our
much is
food.
left?
Yeah.
How much is lost?
At the end.
Yeah. 1,000.
Should be 1,000.
1,000?
Yeah.
Excellent. That's very good. That's 1,000.
Hey, but
Everybody pass.
It took me
Everybody
3
pass.
times to pass chemistry.
I read it as each gram with thousand.
Any question? No? Okay. Well, so that's the end of the material. So the post-class questionnaire or quiz, it does not reiterate. It is supposed to kind of an open-ended of the student. I hope you're gonna go home and research more and think more about what we learned today. So, but first, what we learned about the law of conservation energy. Can someone reiterate it?
It's not lost, it's just transferred.
Not loss or transfer.
Already exists.
It only exists, neither created or destroyed. Very good. What one thing you can do to conserve energy? We saw different type of energy.
Just sit in my chair.
Sit there. Take a nap. Take a nap. Come with
Okay, cool. Great.
Turn down your AC.
Great. And then what question you may have about energy, but that will not cover in this presentation.
I got something. Well, what if you are a scientist who believes in creation
Yeah,
as opposed to the Big Bang Theory?
I know. I'm not
How
gonna
do
decide.
you have many conversations with those types of scientists? How do you deal with that? I mean, it's got to come up.
There's, of course, there's, I think, Scientology, the Christian scientists. But here's the thing: when we talk about the Big Bang Theory, I'm a Christian, by the way. So the question is that Big Bang Theory, that energy, what created that energy? What is that? Nobody knows. It's a Big Bang, but is it an explosion? Nobody knows because there's no space at this time. Time is zero. And in the Bible, God is a God of time. He controls time, right? So this time is unrelative in the, how you say, theology sense. For us, we're living in this known universe, the physical universe that we was exiled to. And so this is what we have, but here this is the point where I call it the unity point, the point of unity. And the point of unity is beyond our time, we was not there. But we carry within it the energy. We live in the same new universe, and that energy was not created, not destroyed. So part of that unity time was in us. It's the light of the world. Anyone will talk about it? So this singularity may be a different universe, a multiverse, right? A different universe, different dimension. But at this point, there and only there if we can go back to that point, but no telescope can be able to capture that light anymore. So it's a big mystery. So what do I reconcile with the Christian scientists, or me myself, is that at that point right there is where the creator, the true creator, exists. Is the intersection of different universe, and there is the one who created. The creator
Thank you.
is there. But can you find that light? Scientists want. NASA want to find that light. They can find lights here and here. They come up with different model of the universe, different donut shape, look, different theory. But overall, there's a mystery. So for our 100 years on Earth, we use scientific knowledge. We do use this, right? We harvest this energy here, fusion and fission, for our daily life. That part of our role here that to subdue the Earth. And the Earth have atoms like water, hydrogen, oxygen. As a scientist, we will use the knowledge that we have. But we do search for the perfect being, as God. So is that the...
No, thank you. Very well. Thank you.
Yeah. Okay, and then the last very interesting question. Thank you. What's the new knowledge about energy you gain from this class?
I'm not a chemist.
Okay.
All of it was
Well,
beauty. all of it was new to me. I mean, I don't remember, I'm sure I learned it at one point, but
Yeah.
that's all.
Yeah, I learned way
In
more.
one ear
than
and
I
out
ever-
the other.
Yeah, way more. This was like, thank you.
Yes,
Very
thank you
good.
very much.
Tim, you wanna take like a 5.5 minute break? You wanna go next?